Okay, let's get started. Welcome everyone, and good morning from the Netherlands. Welcome at today's webinar about how to unlock the power of legacy systems with Apache Kafka. So my name is Joey. I'm the host of today's webinar. And we also have Jeroen van Disseldorp. He's our CEO of Axual, and he will be giving the presentation of today. Good morning, Jeroen.
Good morning, Joey. How are you?
I'm good. How are you?
Good, good.
All right. So the topics that we're going to cover today are as follows. You can go to the next slide, Jeroen. We do a quick introduction into legacy systems. We will discuss when systems become legacy. We have different strategies for modernizing legacy systems. And we're also going to discuss some reference cases at the end. So without further ado, let's get started.
All
The
right.
floor is yours, Jeroen.
Thank you very much. Welcome, everybody. Good morning or good afternoon or good evening, wherever you are. As Joey said, we're going to look at legacy systems today and how to unlock the power harnessed within them. So let's look first at how IT landscapes build up over time and when systems become legacy. So systems and IT landscapes, they build up over time. Usually it starts with a system that you get introduced into your organization with users operating directly on that system. And then, of course, more systems get added to the mix. And there's just random examples displayed here. As soon as you have two systems, then, of course, there's a need to integrate them. And then more systems get added to the mix. And sometimes these integrations are in real time. Sometimes you also have integrations like a file transfer where periodically you send data from one system to the other. And you can even have homegrown systems added into the IT landscape because nothing was available for your particular use case, for your particular requirements. So you build something yourself, and of course that also has to integrate then into the existing landscape. And this is usually how landscapes get built up over time. So heterogeneous landscapes are more or less the norm, with many custom integrations being built over time to resolve the required information exchange between the systems. Now, who actually uses legacy systems? Of course, there's different sectors that have built up such landscapes over time. For instance, a government. A study of Dell revealed that more than 70% of federal IT decision makers in the US, Germany, UK, Japan, Brazil, and India, they use outdated software. Half of the government representatives surveyed said that they even have a legacy software that exceeded its end-of-life date. And they cited COBOL as being the most popular language among governments, even though that was developed over 60 years ago. Another category of companies where a lot of legacy is found is in banking. A shortage of developers in COBOL is probably well known as well. Many banks have developed systems over the days in COBOL and are now stuck with that legacy. They still run well, they function well, but they have to keep updating them to keep up with latest product and technology developments. Yet another sector that has built up a lot of legacy over time is the energy sector, where grids were constructed a long time ago, mostly in the analog days, but nowadays in the modern IT age, they have to become digitized. And then you're stuck with integrating the legacy systems together with the modern IT age. This also is the case in transport, particularly in railroads, where due to high safety regulations, many of the rail control and planning systems, they were developed decades ago, and they still function well. But the front end of rail organizations, of course, they modernize heavily with mobile apps and websites, and that gives challenges on how to connect that old safety-oriented world to the new information era. And last but not least, retail companies, they spend over half of their money on just maintaining legacy systems. And a prominent reason for using legacy is that sales terminals still use really old computers often that can't handle modern software. Of course, these are just a few examples of sectors where you find a lot of legacy systems, but there are many more companies and sectors employing legacy systems, even though their customers expect them to use modern, up-to-date systems. So why are these systems still in use? There's a number of reasons why you still encounter them in IT landscapes. First of all, the old systems, they usually still work. So many of these systems are important to business and to daily functions. They were created years ago when standardized apps for business processes weren't available or not available yet. And replacing them simply because they are outdated is not always viable. So these systems are still in use because they perform and they do well. They serve the required functionality and can even be more reliable and exclusive than modern systems. Another reason why legacy systems are still in use is because they are very familiar. This is actually one of the most common reasons. Legacy systems provide you with a feeling of familiarity and comfort, and people are familiar with how the system works. It's very predictable, workflows are smooth, they help the organization carry out the daily tasks, and they don't have a lot of bumps along the way. Another reason is that legacy systems, they may be very efficient for specific tasks. Some legacy systems, despite of being old and outdated, they work perfectly fine. And most importantly, these systems are typically designed for maximum capacity and remain reliable and durable in most cases. Although they might be difficult to maintain, they're still efficient in carrying out day-to-day operations. A fourth reason is business continuity. Because you have these old systems doesn't mean that you have to update them, because that will definitely give you outages and migration headaches. So just simply keeping them in daily operations gives you continuity of business. Changes are very costly. So being aware of cost and change cost is really important around legacy systems. Maintenance can cost a lot of money in the long term, but in the short term, doing a migration is always more costly. So some organizations just keep outdated systems because they have invested in them heavily, and they may not even have gotten out all the money that they invested in it. And last but not least, changes are also risky. So if you modernize a legacy system, it can be very complex, can be very time-consuming, resource-consuming, risky projects. So some organizations simply don't have the skill set or the will to move and replace these old systems. So, but when are these systems becoming troublesome? Because obviously, well, you can handle them. They work predictably. They can work nicely. But there's, of course, this modern era that has come with websites, with mobile apps, with storefronts, APIs, that somehow has to connect to this old world where records are kept, customer information are kept, orders are kept, assets are controlled, and this often leads to integration challenges. So trying to connect the old world to the new is often when legacy systems really become labeled legacy. And then in such cases, they are perceived to slow down innovation. Actually, there's 4 categories of when systems become legacy. Some of these old systems are heavily patched and completely unmaintainable. No experts are available anymore. And sometimes they've been so heavily patched in the past that nobody dares to touch it anymore. So an example that we have is a customer that came to us with a lot of business processes developed in Perl, but it was very hard to find Perl developers anymore. Another reason why systems can become legacy is end of life or unavailability of updates. So when a vendor decides to not continue the software product anymore, they usually declare an end of life period, and at some point the software becomes unsupported. And this is something that really prevents innovation and forces organizations to create new solutions. I think of when Internet Explorer became end of life, a lot of enterprise applications were built in the past based on Internet Explorer technology. So when that was declared end of life, that slew of applications really had to be dealt with. A third reason is outdated architecture. So when you're dealing with obstacles caused by legacy code, architecture and data, that is something that you really need to handle. And an example would be COBOL, already mentioned, used a lot in finance and in government. Old systems that, well, they work really well, but sometimes they fail to keep up with modern technologies, with modern protocols to integrate with the technology world of today. And last but not least, the inability to scale. This happens a lot with older systems, which may have limited hardware. And I have an example here with IBM systems mainframes. That doesn't mean that IBM systems mainframes are by definition unable to scale, but they often run on older hardware. So then companies are forced to make a choice how to scale the requests that the systems need to be able to handle in real time. We had a customer that, for instance, did transaction processing on an IBM mainframe, and they used to have a requirement that all data needs to be fetched from the source, which was in their case the IBM mainframe. But then if all mobile phones with mobile banking apps start to query in real time the actual balance from the bank accounts, it just simply overloads the mainframe. And that's not what it was intended for. So inability to scale is something that is not really technology specific, but may happen around these mainframes that need to somehow feed information into millions of users potentially. So then when you do mark systems as legacy, what's the risk of keeping them and not changing them? There's also risk associated to it. So one of the risks is, of course, the incompatibility with modern technology, as already discussed. That means that you are limited in your integrations and also limited in your functionality. Another risk is the inability to reuse data. This can cause data to be locked up in silos. A data silo is a repository that cannot be integrated or shared with other parts of the business. And many legacy software systems can be seen as data silos because they have a difficulty integrating with other technologies in the organization. And that, of course, leaves value of that particular data on the table, unable to be used. A third risk is the hindrance of business performance. If you have legacy systems running and they work really well, that's all fine. But at some point, if you need to change the systems and they can't follow up with the changes needed, then of course it can become a hindrance of business performance. And in such cases, you can even get outperformed by your competitors who do manage to reap the benefits of modern technologies. Operating costs. Well, obviously, if you have many legacy systems, operating them can become costly over time. So they won't get updated by the developers anymore. Knowledge is hard to get. You have to really know what you're dealing with in order to be effective and efficient. And these costs can sometimes outweigh the benefits of maintaining the status quo. A fifth risk is security risks. So legacy systems don't receive the technical support or updates from their developers, and they can depend on outdated security measures. And that makes them vulnerable to data breaches, which can cost a lot of money and can also give negative publicity. And last but not least, legacy systems might not be up to standards with the data compliance regulations. And of course, failure to comply can lead to high fines and other penalties. So how to deal with legacy systems? There's actually some different strategies that you can use from relatively low risk to relatively high risk or high impact for modernizing legacy systems. The first one is to encapsulate the legacy system. And encapsulating means to wrap it behind an interface. And this is the most cost-efficient and fastest method. It does not solve the maintenance issues, so you still maintain the legacy system, but at least it unlocks the information contained in the system and makes it available to others. Another way to handle legacy systems is to rehost, which is a synonym of lift and shift. So you run it somewhere else without any modifications. This can lower costs because of a simpler environment or other kinds of hardware underneath, and can bring additional security benefits. A third way to handle legacy systems is to re-platform them, which means effectively running them on a different platform with minimal code changes. So some code changes may be necessary to run it on something else, but it's really minimal. Overall, this can lower cost and allow the use of modern technologies like cloud environments. You can also refactor your legacy systems, which means optimizing it without changing the behavior, taking full advantage of cloud-native features if necessary. You can re-architect, so you make a complete new architecture and rebuild your system in that architecture. Rewrite the entire application, so embrace modern technologies, DevOps, microservices, etc., and rewrite your system from scratch. Or if you really want to go all the way, you re-engineer the entire application, maybe as a new system that replaces the old one in the long run. Of course, the impact and the project risks associated with every method, they go from low to high. So today we'll not visit the far right side of the spectrum, but we'll more focus on the left side of the spectrum, which is how to encapsulate legacy systems and unlock the data contained within them and make that available to the rest of the organization. And there's, of course, two different ways to do that in the modern age. So the two ways to encapsulate the data and to unlock the functionality of the systems is through APIs and through events. Well, there's been a lot of questions recently about when to use APIs and when to use events. So before giving some examples, let's first dive into the differences between APIs and events. So we're going to do that with an example of mobile banking to illustrate when to use APIs and when to use events. So let's look at an example of mobile banking. In this case, you see a customer that approaches a bank API behind which is a mainframe to do the transaction processing. And the customer uses a mobile phone to do all the calls to the bank API. So let's assume that he wants to transfer money. In banking terms, that means initiating a payment. Of course, that payment is first received by the bank API, which then validates the customer. And if the customer is validated, then the init payment command is sent to the mainframe, and a new order is there created for the transaction to take place. Now, of course, the API call can return with a status of accepted. And when it's accepted, then it will happen asynchronously in the background. But let's, for this use case, assume that, well, we execute the order first. And as soon as it's executed, we will send the result of the execution back in the API call. This is a very common case where the customer just sends the initiate payment command and gets a result of this succeeded or the transaction did not succeed. Okay, so the transaction is finished, but after such a transaction, banks need to take care of a lot of things because when transactions happen, then different things need to happen in the background. For instance, a timeline needs to be updated from which the mobile banking app gets its transactions that displays in the timeline. Customers may want to be alerted about transactions that took place. Fraud detection needs to take place. Accounting needs to happen. Personal finance management needs to happen because customers want to know what categories of expenses they spent their money on. And of course, the bank has managerial info that they also need to update for these transactions. And there's different ways of handling that. So let's suppose that we use an API in the middle. So some API which the mainframe then calls to notify, in this case, the timeline. This means that if the notification is sent, the API then forwards the call to the timeline, making sure that the timeline that implements the same API call also gets notified of the transaction that just executed. But if you do that for timeline, then that automatically means that you also have to do that for all the other applications that need to be updated about the transaction that just happened. And that has a lot of downsides because now all of a sudden the mainframe needs to know all its consumers. Calling other systems is not really core banking. Failure scenarios are very complex. So for instance, if timeline is unavailable or fraud detection could not happen immediately, so how do the other systems need to behave or respond? And if you see here, there's actually two commands, new order and execute being done by the mainframe. The rest is all notifications. So that means that communication becomes a heavier burden than the actual transaction task execution. And this in general is really a hell to manage. So let's look at an alternative on, so when we put Apache Kafka in the middle, so now there's not an API, but there's a full-blown event platform in the middle. A mainframe now only needs to send a transaction executed event to Apache Kafka. This is sort of like an announcement to the rest of the world that the transaction took place. And then from there on, Kafka will make sure that everybody subscribed to transaction events get the event asynchronously, which means that the transaction processing can resume on mainframe while all the notifications are being handled by all the derivative systems. So that means that in this scenario, the mainframe doesn't need to know its consumers. It's really fire and forget. So the mainframe can get on with core banking, simpler failure scenarios, and communication is now all of a sudden much lighter than task execution because you have only one arrow coming from the mainframe to Kafka, whereas the other two still remain. So now all of a sudden the transaction processing gets the majority of processing power again. So this is just to illustrate how what the difference is between APIs and events. To wrap that up, so APIs in our situation were really logical and make sense for the customer bank API mainframe in this case. because there's one party that requests another party to do something. And in this case, the customer, and the customer is waiting for the reply and also prepared to wait for the reply. So he calls the bank API with a specific intent, and this results in a many-to-many network of interactions, because any customer can approach any bank API, so to say. But they always call the bank API with a specific intent. On the other side, we have events. And the events where they really made sense to signal the transaction execution to timeline, to fraud, etc. And that really set in motion everything that needed to happen, but was not part of the customer's intent in this case. So the customer intended to transfer money, but the customer had no intent specifically to update a timeline or start a fraud detection process or to update the bank's managerial information. That wasn't part of his API call. So in fact, that could all be done asynchronously through an event sent from mainframe to Kafka to all these systems. And what you then get is asynchronous processes triggered by data changes, which can be really compared to if this then that for business. So if a transaction executed, then fraud detection needs to take place. That would be a logical process step, which is here implemented through event processing. So with this little sidestep, let's go back to our legacy systems. So how to apply this to our legacy systems? Well, in this case, APIs are really used to call the systems. So to command them to do something. So update customer, change order, or store measurement, delete an asset, or update alert settings. These are all point-to-point calls being done by modern systems to an encapsulated API to approach the legacy systems, which is all fine, because here the similar case is that all these modern technologies, the website and the API and the store, they can wait for the result. And they want an acknowledgement of the fact that the command was executed on their behalf. The other side of the coin was that data gets updated in those store systems, and that the data changes would be emitted through Kafka. So examples of data changes that could be emitted through Kafka would be the reverse of the commands that you just saw. So customer updated, order changed, you could have a measurement received, an asset deleted, or an alert sent. These would be typical events that can be sent basically to any system. So it's not to any specific system. Any system here can subscribe to Kafka events and then receive them as they come in. And the usual way to unlock these data sources in the different systems is through connectors. So there's actually a bunch of connectors that Kafka supports out of the box. There's a whole slew of connectors available by vendors in open source. And you can get connectors as a standardized way to export the data from your legacy systems onto Kafka, but also to export them from Kafka into target systems. And these can be any like S3 or Elasticsearch or Snowflake, any target systems that you want to export them to. Now, given these connectors, you can expose practically all kinds of business events in 7 steps. So let's look at these 7 steps and how you can export your data from legacy systems to any kind of target system. So let's start here on the left. You have a source system, and the first step obviously is to find the right connector for you. So what legacy system are you exposing? What kind of data source is it? Are you tapping into the business layer of the application, or are you tapping into the data layer, the database layer of the application? Find the right connector and make sure that its data, the legacy system data, gets exported onto Kafka. Then, of course, you have to see what the raw data schema is. If you tap into a business layer, this could be a business event already, But if you tap into a data layer, into a database, and you do change data capture in any way, then obviously you're often stuck with the data format of that particular database, which may or may not be usable by a target system. So that's why we call it the raw data schema here. It's whatever you can get out of the legacy system onto Kafka that you have to work with. Then, of course, you have to decide, what your exposed data schema needs to be. Is there a big conversion between, fields from the source system and fields expected or desired by the target systems? If there is a big difference, then obviously you have to find a way to map the raw data onto the exposed data schema. So if you have to translate technical fields, then this is where the technical field translation happens, and you translate it into something that the outside world can understand. So let's say asset type 3 won't mean anything to a receiving system. But if you modify asset type 3 into a logical meaning, which could be, I don't know, a smart meter, then all of a sudden it becomes clear if you put the smart meter tag or an enumeration in your target message. Then of course that translation needs to happen. So you have to write your transformation logic, which can be done in many different ways. Basically, you get data from a Kafka topic and you transform it and output it to another Kafka topic, and that would do the translation from the source system schema into your exposed data schema. But you then review the data cleanliness and accuracy, because obviously you want clean data and valid data to go to your target systems. And finally, you hook up the consumers, and this gives you your entire data path from source to consumers in the modern world. And this is what the result could look like. So you could get a complete flow from left to right here, where the green boxes are applications that produce or consume information, and the yellow boxes are Kafka topics, which contain the data streams and the data elements that you produce and consume. So let's break down these application types for a bit, so you can see how you can construct them. Applications can also be of multiple types. You can, of course, write your own applications, which gives you custom code written in Java, Python, .NET, or any other language to connect to Kafka, which you can run on your own platform. And often you have multiple teams around the Kafka platform. So usually these applications run on the team's own platforms. But you can also make it easier for these teams to run integrations by using these connectors, which give you a low-code kind of configuration way to define integrations and to run them. And there's a few examples in this screenshot. Particularly here, there's a source connector and a sync connector for patient records and for health data, which are configured, set up. They import information from some patient record source, and they export information to some database sync, where the user only has to configure the source and the target systems, and then press play, and the connector automatically takes care of importing the data, putting it on Kafka, and the second connector exporting the data and sending it to the target system. But of course, then you still need to handle your transformations, and transformation could also happen well in different ways. You see two transformations happening here. One transformation takes care of sorting information, making sure that particular messages of a specific type end up in one topic or the other. And the other one does a join of two streaming topics and make sure that patient record information is matched with measurements that are flowing in this particular example. And we also have a technology called KSML, which allows you to easily specify these kinds of transformations. In fact, let's look at a few examples here. So you have different kinds of source connectors, hook up any system and any source system and any target system. And you'll also find these connectors on our website. These are pretty standard and are delivered as part of the Kafka platform. And the other technology shown was KSML, which allows you to specify really easily in a combination of YAML and Python code what needs to happen with incoming messages. And in this particular case, there is a filter application shown on the right, where all messages that have a color field of containing blue to be passed through, and the other ones are rejected. So that's a really easy way to specify what needs to happen in such a transformation step. You can also think of fields that need to be transformed from one value to the other, filter out fields, join messages with messages from another topic, so you get data enrichment. That all is possible with these kinds of transformations. And that gives the entire platform that we offer. So this is all offered in a standard package with a streaming layer that takes care of all the data logistics, with a governance layer that allows you to define these connectors and the transformations, where DevOps teams can log in and maintain their own piece of the platform. And we often say that, well, the streaming layer combined with the governance layer is what actually makes a complete enterprise streaming platform. So let's look at a few examples of customers that have done this in the past, that have really unlocked legacy systems and use the data actively in modern landscapes. First customer that does this is Eneco, a major energy player in the Netherlands. They started out with Kafka in 2019. And one of the first use cases that they created was the unlocking of CRM information through a merger that they did just before. They had multiple CRM systems, and that led to confusion in the front end, because not all of their front ends were consistent in displaying customer information. So they unlocked the two CRM systems that they had, made a application that joins all the updates from one of the two systems into a consistent and stable customer view, which was then displayed in the internet front ends that they had. After that, they made many other use cases on the platform as well, even exposing data from the heat grid that they also operate. And by combining the information from people's thermostats and the information from the heat grid, you're also able to save a lot of energy by making smarter decisions in when to heat up the grid. Another customer that has really focused on unlocking mainframe information is Permanent ESB. They selected our product recently because they want to unlock the information they have in their old mainframe to the rest of the bank. And actually a lot of, or major part of their digital transformation journey is based on this unlocking of the mainframe information to the rest of the banking landscape. And they're using Axual platform to unlock that information and to process the information from mainframe before exposing it to other parts of the organization. And last but not least, the Dutch Post, PostNL, they are migrating legacy applications to a new logistical brain. That brain maintains the status of where parcels are, but it did not yet send customer notifications. So they're now hooking up the system to Axual platform, and through KSML, they do all kinds of transformations that ultimately lead to notifications being sent on people's mobile phones. That project got started late last year and is expected to go live just after summer. So 3 great examples of customers that really actively unlock the information from their legacy systems and really make sure that the value in those data elements are actually made use of. And that gives us the end of our presentation. So are you interested in modernizing your IT landscape? We can have one of our Kafka experts maybe help you assess your legacy systems, discuss your environment, assess the possibilities, and potentially support your data unlocking or migration through Axual platform. And with that, I give the word back to Joey.
Perfect. Thank you very much. And I think that was very useful for our attendees. And I think, Jeroen, it seems like that no matter how old your systems are, you can connect them to Apache Kafka. Is that right?
Well, in most cases, yes. There's probably in every system some sort of a way to interact with it. They may not be all up to modern standards, but if you find a way, then there's bound to be a connector available for your legacy system. Or if there's not one available, you can write one yourself, or you can have us write one. And that will also give you the ability to unlock your information and put it onto Kafka.
Cool. Okay, so we do have 5 minutes left for a live Q&A. So if you have any questions, feel free to ask us right now. There is a Q&A pop-up available within Zoom, so you can just type in your question. And I see already a couple of questions coming in. The first one for you, Jeroen. Can I also build this with open source Kafka, or does my setup miss functionality?
Oh, you can definitely build this with open source Kafka. The connectors are sometimes they're proprietary, sometimes they're open source, but the runtime they work in, which is called Kafka Connect, that is open source and part of the Kafka package. So if you use Kafka Connect, you can definitely use all kinds of connectors. You can build one yourself, or you can procure one, or you can get one from an open source repository somewhere. But as soon as you have that, you can start it up and you can manage it. So that's all possible. You do have to find your way around the command line a little bit, because Kafka Connect is only controllable through a REST API. So you have to be able to send curl commands for those that know what curl is. But if you do, it's perfectly manageable through the open source packages of Apache Kafka.
All right, next question from Lieke. Can Kafka improve the performance of my legacy systems? And if so, how?
It's well, the example that I showed about mobile banking is an example which is really implemented also by a few of our customers, where the legacy system used to be overloaded with queries from mobile phones, and by shifting the burden of notifications to Apache Kafka and to further downstream systems, a lot of the load was actually taken away from the legacy system. So in this case, the mainframe, which really improved the mainframe. So yes, definitely Kafka can help in alleviating the burden there.
Cool. All right, next question from Marcus. Axual platform is Strimzi based, right? Have you taken over environments that were running on open source Strimzi before?
Well, yes, Axual platform is definitely Strimzi based, which gives our customers the option, so they can continue running their own Strimzi, or you can have it replaced by Axual streaming layer. The Axual streaming layer is actually based on streaming, so migration from Strimzi to Axual streaming is not a big deal. So we provide support based on just open source Strimzi. So some customers come to us and want a supported version of Strimzi. And in those situations, we can just support their open source Strimzi installations, so no need to replace any software. But we can only do that on a 5x9 basis. So in office hours, you can call us, and then we'll help you fix the problem. This is not available for 7x24. If you want 7x24 support, then you really have to embrace actual streaming. Because it sort of narrows the configuration mistakes that you can make. And 7x24 means often that customers want to run it as a mission-critical system. And if you want to run it as a mission-critical system, then obviously you do want a bit of a straightened-out configuration, which leaves no room for configuration errors. And that's what we provide with actual streaming, along with a few other components that help you realize your streaming layer, but those are completely optional. I hope that helps.
Right. I see another question from Peter. Who decides who gets access to which data?
That's actually something that, in our platform is done in the governance layer. I go back to the picture quickly. Is that possible? I think it is, but my system is a bit slow, it seems. But the architecture picture with the 3 layers, here you see that the streaming layer itself is basically Kafka, with Strimzi indeed as the operator to manage it in Kubernetes. We have components to do message and offset and schema synchronization on that particular layer. So that would be one of the additions that actual streaming provides if you want to have a multi-cluster system synchronizing messages where applications don't need to know about specifics on where a producer is producing messages, but they just want to consume anywhere. Then actual streaming is really the layer where this data logistics is being handled. The actual governance layer is where teams log in, and this is where ownership is assigned. So who is owner of what particular topic? If you are owner of a topic, that's what we call a data owner. And as a data owner, you get to decide what schema to apply to a topic. And also when you evolve certain schema, but also one of the rights that you have is to decide what applications get access to your particular topic. So somebody else, owner of an application, can log into the governance layer. They can register their application, upload their security credentials, and then as soon as your application is configured, so the public key is known, or the SSL credential is known, or some other credential is known, then you can start to request access to a particular topic. The respective data owner will get a notification that this and this application operated by this and this person requests access to your topic, either as a producer or as a consumer. If you approve, do you approve, yes or no? Well, if you approve, then you get access right away. So all the ACLs on Kafka are set in the proper ways. And if you reject, then of course you can send a reason back to the requestor on why you rejected that particular request. And that is all managed automatically. So if any authorization changes in the governance layer, automatically the ACL on Kafka is updated for you. So there's no proprietary features like RBAC or anything being used here. This is plain open source Kafka managed by actual governance.
All right, good stuff. I do have one final question. How long does it on average take before I can get some first data from our systems?
Oh, good question. Well, we've done numerous POCs in the past, and usually we try to make a POC work within a small number of weeks. That depends really, of course, on where the legacy system is located. If it's in your back office somewhere, then it's often, well, the most time consumption is then the requesting of a VM or the requesting of other hardware to make the export work or to make the POC work. That's usually where the most of the time is spent. But setting up a Kafka platform, setting up a connector and exporting the data usually is, I don't know, about 25% of the time. And the rest is just managing the hardware, managing the organization to get the POC in a place where it needs to be.
Okay, I think that's it. I see no more further questions.
All right.
Let me double check. No, that's it. Okay, I will make sure to share the slides and the recording with each and everyone. And if you do have any questions after the webinar, feel free to just reply to my email. So that's it for today. Thank you, Jeroen, for the great presentation.
Thank you, Joey.
And talk soon.
Thanks, everyone. See you.
Okay.
Bye-bye.
Bye-bye.